All right, so number 1, the yearly number of books. This is the Unit 6 review worksheet that looks like this. Yearly number of books read by book club members is normally distributed with a mean of 25 and a standard deviation of 5. So at that point, I go ahead and I draw my standard normal bell curve. The mean is 25, standard deviation is 5, so this is 30, 35, 40, 20, 15, 10. Okay, what is the probability that a randomly selected book club member has read between 10 and 35 books? Well, this is 34%. This is 34%. These are 13.5, and I'm going to leave off the percent just because of space. Then 2.35, 2.35, and the very ends would be 0.15 and 0.15. Here's 10, and 35 is right here. So we're just adding up these percentages. So this is 68, and then I think this would be 95 altogether here, plus 2.35, so it should be 97.35. Is that what you get? Okay, 97.35%. Or you could do it as a probability and say 0.9735, or you could do it as a decimal rather. Okay, number 2. The heights of waterfalls in Tennessee are normally distributed, so again it means it's a bell curve situation, with a mean of 50 feet and a standard deviation of 12 feet. So I draw at this point another one of these. Mean of 50, standard deviation of 12. So I add 12, add 12, add 12 going to the right, subtract 12, subtract 12, subtract 12 going to the left. That one's kind of slanted. All right. What is the probability that a waterfall chosen at random will have a height less than 86 feet? So again, I'm just using this because 86 is one of my numbers. I don't have to worry about a z-score here. So the only thing more than 86 feet is the 0.15% over here. That's the only thing higher than 86 feet. So if we're looking for the probability of a height less than 86, that means everything other than that. So 100% minus 0.15 is going to give me 99.85% chance, or 0.9985. Questions on that? Okay. Number 3. In a certain normal distribution of scores, the mean is 90 and the standard deviation is 7.3. Find the z-score corresponding to a score of 103. Okay, so 103, here's the formula, remember, and it's right on your review. 103 is my score that I'm looking up. The mean is 90. The standard deviation is 7.3. So I'm doing 103 minus 90, which is 13, divided by 7.3, and I get 1.78. The z-score table always does tenths only, so I'm just going to call that 1.8. That's the z-score. That's not the probability, that's the z-score. What that says is a score of 103 is 1.8 standard deviations above the mean. If I wanted to know a probability of getting excuse me, a score of 103, that's when I would go look it up on here. In other words, z-score is what this formula gives me and what I take to the table. The things that are in this table or this chart are the probabilities of various z-scores. Still have some people confused between the probability itself and the z-score. So the z-score is 1.8, and that's all I was asked for here. What is the mean? This is number 4. What is the mean and standard deviation of a normal distribution that approximates the binomial distribution with 34 trials and a probability of success on each trial of 0.15? Well, The whole part about approximates the binomial distribution just means uses these formulas. Okay? These formulas are formulas for a binomial distribution. So, we're just plugging in x bar n times p, so that's 34 times 1.15. And that gives me 5.1. Actually, it's not even approximate, it's exact. And baby sigma, lowercase sigma, it starts with NP, and then it's times 1 minus P. So NP I already found up here. So this part right here is 5.1. 1 minus P, 1 minus 0.15 is 0.85. It's like 100% minus 15% is 85%. So I'm doing 5.1 times 0.85, and then I'm taking the square root of that. 2.08. When in doubt, round to the hundredths place. If it doesn't say, just go ahead and go to the hundredths, which means 2 decimal places. Give an example of an experimental study. Okay, keep in mind that an experimental study is one where the person doing the study has control, no pun intended, over who is in the control group and who is in the experimental group. So you could have a lot of things. An experimental study could be, I go to a school and I tell half the students you're not allowed to have a regular lunch, you're going to have peanut butter and jelly for lunch, and I give half the students, they're not allowed to go to the cafeteria, they can only have peanut butter and jelly, and then I do a blood test a week later to see how this affects their blood sugar or something like that. If I'm selecting who gets the lunch that is peanut butter and jelly and who gets to go to the cafeteria, that's an experimental study. So anything where the person forming the study gets to choose. If I do a study where I'm growing plants and I give half of them water and I give half of them Miracle Grow in their water, I'm the one choosing which ones get the Miracle Grow in the water. So I'm the one forming which one's the experimental group and which one's the control group. So that would be an example of an experimental study. Okay, tell whether the study is an experimental or observational study. You want to study the effects of playing a practice round of golf has on a golfer's ability to play well in the state tournament. The scores of each individual in the state tournament are analyzed. The control group is individuals who did not play a practice round. The experimental group is individuals who did play a practice round. The assumption here that what I'm looking at is the scores in the state tournament is that I'm deciding to analyze this after the tournament has been played. So I didn't get to choose who played a practice round and who did not. Okay? So that means I'm not the one dictating who is in the control group and who's in the experimental group. I'm looking at who did that and who didn't do that, and I would assume it was their choice whether or not to do that. Okay? So the control group is the people who didn't do it, and the experimental group is the people who did do it. That's observational. If I had said if there was anything in there about me telling people, okay, you guys, you're going to go play a practice round, and you other folks over here cannot play a practice round, then it would be experimental. All right, on the back, make a histogram showing the probability distribution for C. First thing you have to do on these is figure out what your sample space is, like what all the possibilities are. The possibilities are Snickers, Skittles, Kit Kats, and Twix. So I'm going to have a little chart here, probability of a Snickers, probability of a Skittle, probability of Kit Kat, and probability of Twix. And I'm going to find those probabilities the same old-fashioned way you did it in like 5th grade. Just the number that you have over the number, the total. So I need to figure out the total. Excuse me. It's 48. Is that right? 58, I'm sorry. I'm doing it in my head and I'm doing it wrong. 58, that sounds right. Yeah. Okay. So Snickers, I have 15 out of 58. Skittles, 22 out of 58. Kit Kats, 13 out of 58. And Twix, 8 out of 58. I'm going to change each one of those to a decimal. First one is 0.26. Next one is 0.38. Next one is 0.22. And last one is 0.14. Okay, so Snickers, I'm going to say, since I've got biggest number here is 0.38 and the smallest number is 0.14, I'm just going to go by tenths. So 0.1, 0.2, 0.3, 0.4. So Snickers are 0.26. A little more than halfway between 2 and 3. Could have gone a little higher maybe. There's my Snickers probability. Skittles, 0.38, goes all the way up here. Kit Kat, 0.22. And Twix, 0.14. Okay, circle one, symmetric or skewed. I would say that's skewed because symmetric has to have symmetry around the middle. It does look like it could maybe have some symmetry if it keeps going this way, but we're talking about the middle of the graph. Okay, so this looks skewed slightly. It's your mean, your highest point is over here. Not really your mean, but your highest point is over here. Your greatest probability is to the left of center, not right in the center. Okay? Does anybody have an LED graphing calculator I can borrow? Thank you. All right, on number 8. Thank you. Sorry, is that on you? Number 8, you could do it one of two ways. You could do the formula. This is saying I have the probability of K successes in N trials. And number 8, it says K is 10, N is 17, and probability is 0.39. So this is the formula I'm talking about. If I can get my marker to write. Let's try a different one. That's the formula. So if I want to put that in the formula, I would do 17, choose 10, which is just saying, that's saying the number of different ways that I could pick 10 objects out of 17. 0.39 to the 10th, and 0.61, which is the complement of 0.39. If you have a 39% chance of success, that's a 61% chance of failure, and that happens 7 times. So this is what I would put in my calculator if I wanted to do it by, sort of by hand, I guess you would call that, if I wanted to use the formula. If I wanted to use the calculator, if I have my graphing calculator, I can just go in top of VARS, there's distribution. I go to the distribution. You got to go down for a ways. We're not the normal PDF, it's binomial PDF and binomial CDF. PDF is, I like to think P is for per, like for an individual. Okay, PDF is the one for just one, because this is only asking me about the probability of getting 10 successes, not 10 or greater, not 10 or fewer, just 10. So this is binomial PDF. If you're doing it in a calculator that asks you to put it in commas, you put in the total number 17, the probability of success 0.39, and then the one you're asking about, N, P, K, in that order. If you put it in the wrong order, it'll do the wrong thing. On some of them, it will ask you like this. It'll say that what are your number of trials? That's 17. Probability for each trial is 0.39, and the x value is 10. And you see it puts it in that same order that I just had it here. If you could see it all. And I press enter, and it tells me 0.0497. I'm going to go ahead and round that to the hundredths. So that's 0.05. Okay, so I have a 5% chance of getting exactly 10 successes. Now number 9 asks not just exactly about 2, it asks about 2 or fewer. So I could still use this formula, and especially with 2 it's not that bad because I don't have to do too many, but it's asking about 2 or fewer. So I would do probability of getting 2, 1, or 0. Because those are the possibilities if 2 or fewer are the options. So I have an n value of 5. My probability is 0.91, which means the percent chance for failure would be 9%. Remember that how this works is, this is the number of ways I could have success on 2 of them. In other words, I could have success the first and the second time, or the second and the third time, or the first and the third time, or the second and the fifth time. There are different ways I could have success on 2 out of 5. This is the probability of success, and we're talking about succeeding 2 times, which means I fail 3 times, and that's the probability of failure. So here we are saying, out of 5 trials, I'm successful once. Probability of success for 1 time, probability of failure for 4 times, and so on. I would add all these up because its k is 2 or less, and I would find the total. Or I go to my calculator and I use Binomial CDF. CDF, you could think of the C as standing for cumulative. Cumulative is all together, added up, like a cumulative exam at the end of the semester. All right, so I'm going to go to distribution, have an arrow down to Binomial CDF. Can you see that at all? Okay. Press enter, and it's going to ask me how many trials. There's 5. My probability for success each time is 0.91. And my x value is 2. Okay, that's how you would put it in a regular graphing calculator, or not quite as new one. N, comma, P, comma, K. And that gives me 0.006. So if you have 0.006, don't round to the hundredths place, because that would just be 0, and we're not going to have a probability of 0. We're not going to have a probability of 1 or 0. Okay, 1 means it definitely happens, 0 means it definitely doesn't happen. There is a chance this is going to happen. So go ahead and go to the first non-zero number, at least. Okay, let's talk for a second about what if it had been probability of k is greater than or equal to 2, or greater than or equal to something else. If I have, let's say I have, n is 10. I have 10 trials, and the probability for each trial is 0.25. Okay, and I want to know the probability that k is greater than or equal to 7. Okay, if I have n trials, that means I could have success. K is a success, is a number of successes. I could have k equals 0. I could have k equals 1, k equals 2, k equals 3. All the different possibilities are from 0 to 10. Okay, so what you have to realize is that k is greater than or equal to 7, and you don't have to write this out, I'm just making a visual for you, is 7, 8, 9, and 10. Okay, so we could do it with the formula and just add those up. But if you do the formula in the calculator, if you do it by putting in binom PDF or binom CDF in this case, it's CDF because it's greater than or equal to, okay? It's a range of values. You've got to realize the calculator, just like the z-score table, always goes to the left. Always, always, always goes to the left. Greater than's to the right. So if we want to go to the left, that means we have to consider the opposite of this, which is the only possibilities that aren't here are 6, 5, 4, 3, 2, 1, 0. So k is less than or equal to 6 would be the complement of that set. In other words, if I want p is greater than, probability of k greater than or equal to 7, I subtract from 1 the probability that it's less than or equal to 6. Because together, the probability that's less than or equal to 6, which is 0, 1, 2, 3, 4, 5, 6, and the probability that's greater than or equal to 7, which is 7, 8, 9, 10, those together make up 1. Because 1 would be the sum of all probabilities, because something's going to happen. Okay? So if you are asked to do greater than or equal to, you have to look at less than or equal to the number less than this and subtract it from 1. So in my calculator, I would do binom CDF for n is 10, probability is 0.25, and k is 6. And then after I get this answer, I would subtract it from 1, and that would give me this answer. All right, moving on. Number 10, give the percentage of the area under the normal curve represented by the shaded region. You're just looking at what's shaded. This is 2.35, okay? So I got 2.35. This one is 34. This one is 13.5. Had a moment there. And this one is 0.15. So altogether, that's 50%. It also makes sense that half of them are shaded. Okay, over here, this one is 13.5. This is 2.35. This is 2.35, and this is 0.15, or you could think of these two together, remember, are always 2.5. So 13.5 for this one, plus 2.35 for this one, plus 2.5 for these two, equals 18.35. This is 50%. And it does say percentage. I did not write down. What did we get for this one? 0.05, I think?
Yeah, 0.05.
And this was 0.006?
Yeah.
And we said this was skewed. All right, last two, you're just plugging into the formula. That's all you're doing here. And if you could do everything on this review, you're great for the test. So, number 12. X bar is n times p. So 17 times 0.13 is 2.21. Lowercase sigma is square root of np, which we just said was 2.21, times 1 minus p, which would be 0.87. That gives me 1.386, so that's 1.39 approximately. Again, if you don't know, just go to the hundredths. So I would put 2.21 here and 1.39 here. Number 13. N is 396. P is 0.55. So 396 times 0.55 will give me X bar. I get 217.8. Baby sigma, square root of NP, which we just got 217.84, times 0.45. Take the square root of the whole thing, and you get approximately 9.9. Actually, you get exactly 9.9. So forget approximately. And that's our whole review. And this would be 217.8 and 9.9.